Swayam Prabha. Digital India. Educated India.
Welcome friends, welcome to the course Introduction to Sampling Theory. Now in this lecture we are going to start with a new type of sampling scheme. You see, up to now what you have done, whenever you want to draw a sample, the first step is to identify the population, and then you try to create the sampling frame. Sampling frame means you try to identify all the sampling units in the population, and then you try to use a random number table and you collect a sample. But do you think that this type of approach is always going to work? There can be some situation where these things may not really be possible to do. For example, let me take a very popular example of this sampling or this condition. Suppose you want to collect a sample in a forest. For example, you want to know how much is the wood of trees available in the forest. Forest, you can imagine that is a dense place with many trees, bushes, etc. And it may not really be possible inside the forest to go to all the places where you want. It might be possible that the forest is so dense that you cannot reach to all the points in the forest, but you have only one option, that you will try to reach to a point wherever you can do it easily. Suppose there is one place where it is so dense that you just cannot enter into that area. What you will do? Or there is some tree which is on some height, on some small mountain, there you cannot reach. So now under these types of condition, my question is, how would you like to draw a sample? Because in case if you want to measure the total amount of wood available in that forest through those trees, you have to at least collect a sample of the trees, and you have to somehow measure that how much is the wood available in those trees. So now once you cannot reach to that particular tree which you have already selected in your sample, means through the random number sampling, that means suppose if I say, suppose hypothetically you have all the information on the trees, you number them 1, 2, 3, 4 up to and so on, capital N, and you draw a random number table, and you suppose you have to go to the tree number 20. Now suppose the tree number 20 is at a place where you cannot reach. Now what you will do? Now in case if you don't take the observation on that tree, that means you are violating the rule of randomization. Then sample is going to have some issue like as bias, etc. So my question is this: how to take a sample in such conditions where it is not really possible to have the sampling frame before the start of the survey. Under such type of condition, the methodology of systematic sampling help us. And we are going to start the discussion on sampling theory, which is on the topic of a sampling theory, which is systematic sampling. So now what can we do? That suppose I draw a number from the random number table. Suppose this number comes out to be 5. So what I will do? I will simply enter into the forest. I don't know the way, I don't know the route, there is no predefined route. And then I will start walking on that route, on that path, and whatever tree I get at the 5th place, I will try to measure the volume of the wood in that tree. And then I will try to take the next fifth tree, that means the tree number 10. Now, what is your tree number 10? That we don't know unless and until you reach to the tree. Then whatsoever your 10th tree comes, you are going to measure the volume of the wood. And similarly, you can continue to every tree after 5 trees. So, you will have a sample like 5th tree, 10th tree, 15th tree, 28th tree, 25th tree and so on. So, all the trees at an interval of 5. On the other hand, if your random number comes out to be suppose at 10, then I will be taking the first unit in my sample as the 10th tree, that is the tree number 10. After that, I will be taking the next 10th tree, that is tree number 20, and then tree number 30, 40 and so on. And I will try to continue till I get a sample size of the required number. In the total number of sampling units which I have to draw, they are known to us. Okay. So, this is the basic methodology of the systematic sample. And if you try to see what are we going to do, why this is called as systematic sampling, means up to now either it was simple random sampling or any other type of sampling, you just drawn all the random numbers and you picked up those sampling units. But now here you are trying to draw only one number and then you are systematically trying to draw all the sampling units. That is why this is called as systematic sampling. Okay. So, now let us begin with this lecture, and in case if you want to download the slides of this lecture, you can download it from my home page. I have uploaded the PDF version of the slides over there, and the address of my home page is home.iitk.ac.in/shalab/sp. And still if you are facing any problem, you can scan this QR code using any application on your phone. It's any free application, and then you can scan it and you will reach to the same address. And still if you are facing any problem, you can go to any search engine on the internet, type my name, type my institution name to be more precise, and I am sure that you will find my home page, and from there you can download the slides. Right. So, now let us begin our formal discussion on the systematic sampling. So, you see, this systematic sampling technique is operationally more convenient. That is true, because you have to draw only one number and then you have to choose the sampling unit which you can obtain conveniently. So, this is going to be more convenient than the simple random sampling, right. And it has one more property, that at the same time this systematic sampling scheme will ensure that each unit has an equal probability of inclusion in the sample. So, whatever are the rules of drawing the sample, they are going to be followed, right. So, in this method what we try to do, as I explained you, that we are going to select the first unit with the help of random numbers, and then all the remaining units are going to be selected automatically according to a predetermined pattern. Predetermined pattern means, suppose if I suppose my random number comes out to be 5, then after that I will be taking the 5th unit and then 10th unit and then 15th unit, then 20th unit and so on. Right. So, this method is known as systematic sampling. Now, one question comes to our mind, that when are we trying to obtain such observation, and suppose we want to estimate the population mean, then the first question is, how are you going to choose an estimator which ensures the efficiency, that means the variance of that estimator should be as small as possible. And this type of sampling creates a confusion in our mind, that when are we choosing this sample in this particular way, which is not like a 100% random sample. do you think that the estimator that we are going to use will be good? Answer is yes. Now, under this type of sampling scheme, this is a challenge for all of us, that how should we find an estimator which ensures that even when we are trying to obtain the sample in this particular way, the population mean can be estimated using these observations in an efficient way. So now for this, the concept is very simple, that you have done in the case of cluster sampling, in the case of stratified sampling, that you define your estimator of the population mean in such a way such that the variance of that estimator was helping us in ensuring that the proposed estimator is doing well and doing fine. So similarly, here in the case of systematic sampling also, we have to define our estimator in such a way that even under this type of condition, that is going to give us a good value of the population mean. So this I will try to show you after I propose the estimator. Okay, so now let us come to our slides, and now if you try to see how are we going to work. Suppose the units in the population are numbered from 1 to capital N in some order. That is the same way as you were doing up to now, right? This is the same way how you have been creating the sampling frame. But now here the problem is this: the population is not known to us. Means we know the population, where is the population, but it is difficult to assign particular number to a particular unit. But hypothetically, before the start of the survey, I can assume, for example, in the forest, okay, all those trees in which we are interested, they are numbered at 1 to capital N. Remember one thing, we don't know which is going to be the 12th number. For example, in the case of simple random sampling, if you say that we are going to choose the 12th unit, then we know that which of the sampling unit is going to be chosen. Whichever unit that is corresponding to the 12th unit in the population, that will become the part of my sample. Suppose if I say that there are 100 students in the class, so I already have given them a number from 1 to 100, and suppose if the number comes out to be 12, then I know that the 12th number student whom I know that who is that student, that is going to be a part of my sample. So now in this case, we are making an assumption that capital N is expressible as a product of two integers, small n and small k. Well, there can be another condition also, that where this capital N cannot be expressed in the form of as a product of the two integers n and k. So I will try to handle here, I will try to discuss here both the cases, but at present we are going to consider the case when we have capital N is equal to small n into small k, right. So now, in case if you want to draw a sample of size n, what you have to do? You simply have to first select a random number using random number table between 1 and k, and suppose you choose a number which is here I. So definitely I is going to be between 1 and k. So now you select the first unit whose serial number is I, and then after that select every kth unit after this ith unit. As I said, 5th unit, 10th unit, 15th unit, and so on. So now what will happen? The sample will be containing the sampling units who were bearing the serial numbers I plus k, I plus 2k up to I plus n minus 1 times k. Right. So how this will look like? Because I will try to show you through the table. So in this process, what is really happening? That the first unit is selected at random, and the remaining units are selected systematically. And that is why this is called as systematic sampling. In fact, this is called as linear systematic sampling. And in this case, the systematic sample which you have obtained, this is called as kth systematic sample, and k is termed as a sampling interval. That is our terminology, right. So if you try to see here, if I try to take here means population, suppose my population units are say here y1, y2 up to here, see here y capital N, and now n is equal to small nk. And now I will try to arrange all these sampling units row wise. For example, I try to write down here the first unit as y1, then y2, then here y3, and I will continue, and somewhere I will have here the yi corresponding to random number I that we have generated, and I is lying between 1 and k, right. So and then I will continue and I reach up to yk. Remember, k was the random number that you have drawn. Okay, now after this I try to change my row, and I try to write down the next unit yk plus 1 here in the second row, and then I continue to yk plus 2, yk plus 3, and somewhere there will be here yk plus I, and then finally we will have here yk plus k, which is y2k. And after this I will once again change my row, and I will try to write them again. So every row is going to contain k number of observation, and k is the random number that you have drawn from the random number table. Okay. So now the last row will become here like this, y n minus 1 times k plus 1, y n minus k times plus 2, y n minus 1 times k 3 plus 3, and so on, and somewhere there will be y n minus 1 times k plus I, and finally you have here y capital N, which is your here y n k, right. So you can see here what I am doing here now, that I have written all the sampling units in a 2 by 2 table such that every row contains k number of observations, and there are such small a number of rows, right. And now what are you trying to say? You had said that you are going to draw every ith unit in your sample. So now out of these small nk number of values, which are the values that will be included in the sample? You said every ith number. So this is the first unit that will come to your sample, this is the second unit that will come to your sample, and this is the nth unit that will come to your sample. So now this collection of units y k plus I up to y n minus 1 k plus I, this is going to constitute your ith systematic sample, right. And similarly, if you try to see here, means if you try to choose here any other number between 1 and k, suppose if I choose I equal to 2, then the units which are corresponding to this serial number here 2, that will become my systematic sample. And similarly, if you try to choose I equal to k, then this column corresponding to k, this will constitute my systematic sample. So you see how many now possible samples you can have? You can have here k possible samples, and that is what I am writing here 1, 2, 3, here I, and up to here k, and these are my systematic samples. So any of these k possible samples, they can be chosen in my sample, and we are going to conduct our analysis on the basis of the units which are the part of my kth or say ith sample, right. And since there are small k number of possible sample, and since you have drawn this number I between 1 to k at random, so any one of this sample, either the first one or the second one, third one, or say ith one or the kth one, that can be included in my sample. And since this number has been drawn by at random, so the probability of choosing any number between 1 to k will be 1 upon k, and this is what I am writing here in the probability, that the probability of selecting either the first sample or the second sample or third sample or the ith sample or the kth sample, they are simply going to be 1 upon k, and they are equal, right. And if you remember, in the case of simple random sampling also you did the same thing, that when you were trying to do the sampling, and when you wanted to choose a sample of size small n out of a population of size capital N using simple random sampling without replacement, then you had decided that there are going to be n choose a number of samples, and you can choose any sample out of that, and the probability of choosing any sample was 1 upon n choose n. Right. So, the same thing is happening here also. So, now you can ensure that the sample which you have chosen, this is drawn randomly. Now, what I am going to do, that I am going to choose here these samples, and then I will try to find out here their sample means, and these sample means are going to be denoted as, say, for the first sample this is going to be denoted as y1 bar, then I am going to denote here by y bar 2, and then for the third sample, for example, if you choose, the sample mean is going to be y bar 3 and so on. So, the mean of the ith sample is going to be indicated by y bar I, and similarly the mean of the kth sample is going to be indicated by y bar k. Right. So, now just for the sake of an example, suppose if I say capital N is equal to 50, and suppose I want to draw here a sample of size 5. So, then what will be your here k? N upon small n, which is 50 upon 5, which is equal to here 10. So, that means your k is going to be now here 10, and now you have to choose any random number between 1 and 10. And suppose you select a number and this number comes out to be a 3. So, that means you have to select 5 sample units starting with I equal to 3. That means your first sampling unit is going to be the third unit, then 3 plus say here 10, that is going to be 13. So, second sampling unit is going to be the 30th value in the population, then 13 plus 10, this is going to be the 23rd sampling unit of the population, that will become your third unit in the sample. And similarly, if you try to go with 23 plus here 10, this will become say 33. So, the 33 unit in the population will become the fourth sampling unit in your sample. And then finally, you wanted to have a sample of size 5. So, the fifth unit is going to be 33 plus say here 10, which is here 43rd unit. Right. So, this is now becomes my here y1, this is my here y2, 23 is my here y3, 33 is my here y4, and 43 is here my y5. Right. And then I can find out the arithmetic mean of this thing. Find arithmetic mean of these observations. Right. So, now you have got that how are you going to obtain the y bar I. So, now you can see that this systematic sampling has got certain advantages. What are those advantages? It is easier to draw a sample, and often it is easier to execute it without any mistakes. Right. And as I discussed earlier, this is going to be more advantageous when the drawing is done in fields and offices, as there may be substantial saving in time also. Right. And definitely the cost is going to be lower, because the selection of the sampling unit is much simpler. And as we had discussed that whenever you are going to conduct the survey, you have to train your surveyors that how they are going to collect the observation. So, in such a case, much less training is needed for the surveyors to collect the sampling units through this systematic sampling. You simply have to say, okay, go to the field and try to select every fifth unit. Right. Okay. And another advantage of systematic sample is that the systematic sample is spread more evenly over the population. right, because you are trying to take the observation after every given interval. So, the advantage is this: no large part will fail to be represented in the sample, and the sample is evenly spread and cross section is better. The problem in the systematic sampling will come only if there are too many blanks. So, systematic sampling practically fails in case if there are too many blanks, means the units are not available, or the unit which you want, that is not there, right. Okay. Now, this systematic sampling, if you try to see the structure and if you try to particularly observe this table in which I have arranged all the sampling unit, this systematic sampling can also be viewed or can be related to cluster sampling as well as stratified sampling, right. So, first we try to understand how this systematic sampling or the systematic sample can be viewed as the cluster sample or sampling technique, or the systematic sample is going to look like as if this is drawn from the cluster sample. So, now we try to first understand the cluster sampling, and then we will try to understand the stratified sampling. So, you know that when I am assuming that capital N is equal to small n into small k, there are going to be k possible systematic sample. Now, can you imagine that the same population is now divided into k large sampling units, each of which contains small n of the original units, right. Means if you try to see here, what will happen here, that if you try to write down here all the numbers here y1, y2 up to here yk, and finally you have here yk plus 1, yk plus 2 up to here y2k, and up to here finally you will have here ynk. So, I am trying to say here that now I am trying to arrange these units in a cluster like this one. Right. And now what are you trying to do? You are trying to choose here one particular this whole cluster. So, don't you think that if I am trying to say that you try to arrange these units in this form of a table, and then you try to choose one particular column, and we are calling it as a systematic sample, but if you try to see this is my cluster number 1, this is cluster number 2, this is cluster number here k, then you are trying to choose only one cluster in the sample from a population of k clusters. In the case of cluster sampling, what you have done? You have chosen more than one clusters. Now, you are choosing here only one cluster, right. So, now after understanding this thing, I can say that the operation of choosing a systematic sample is equivalent to choosing one of the last sampling unit at random, which constitute the whole sample, right. So, I can say here that the systematic sample is a simple random sample of one cluster which has been drawn from a population of k clusters, right. So, that is the understanding. Now, suppose I say here now this yij is going to be my sampling unit. Now, I have to choose here two subscript, because one of the subscript is going to indicate the row and say another subscript is going to indicate the column. But the same symbol yij we have used in different occasions starting from stratified sampling, and every time this yij had a different interpretation. The same thing will happen in the case of systematic sampling also. So, here in the case of systematic sampling, this yij is going to indicate an observation on the unit bearing the serial number I plus j minus 1 times k, right? And here I will go from 1 to small k and j is going from 1 to small n. So now what I am going to do, I am going to draw a random number here I, which is going to be smaller than k, yeah, greater than 1 obviously, right? So now my sample consists of ith column. If you try to see here in this table here, what you have done, you have chosen this ith column as your sample, right? Now try to find out the mean of all the observation in that column. For example, here if you try to see, you have taken here these many observations here and you are trying to find out their arithmetic mean. So whatever is the mean of this thing, that I'm going to denote here like y bar I, okay. And this is going to be simply here 1 upon n, j goes from 1 to small n, y I j. And this we are going to denote here as a y bar sy, that means y bar systematic. And we are going to consider this y bar systematic as an estimator of the population mean, and the population mean here is given by capital Y bar, which is the arithmetic mean of all the units in the population, that is all. 1 upon a small n k, I goes from 1 to k, j goes from 1 to n, y I j, and this can also be written here as a y upon n k, y bar I, right, okay. And then you have seen here in this table here that the probability of selecting ith column as a systematic sample is simply 1 upon k, that we have discussed in the table. So now if you try to see, you are going to choose one sample from the possible k number of samples, and you are going to choose it at random. So now in case if you try to see here, take here the expectation value of y bar sy, that is simply going to be 1 upon k, I goes from here 1 to k, y bar I, and this is going to be simply here capital Y bar. So I can see here that y bar systematic is going to be an unbiased estimator of the population mean capital Y bar, okay. Now in case if I try to find out the variance of this thing, so variance is very simple. You have a population consisting of y1 bar, y2 bar, yk bar. So you simply have to just find out the variance of this thing, because the variance of this thing is going to be 1 upon k, I goes from 1 to small k, y bar I minus expected value of y bar I, which is here y bar, capital Y bar. So now finding out the variance of this thing is not difficult, that is straightforward. You don't need any algebra, but you need only the concept that how are you going to choose your sample and what are your sampling units, right. So here this y1 bar, yk bar, y2 bar, yk bar, they are simply your here sampling units, and this is in the population. So right, so that is why we have this variance of y bar sy directly here. Now the only question is that now I would try to look into the structure of this variance so that I can make some more conclusion, right. So I try to consider here this quantity capital S square. So capital S square is simply going to be your here 1 upon capital N minus 1 double summation say I n j and y I j minus y bar whole square. So this n is going to be now here small n k. So I try to take this n minus 1 times S square on the left hand side, and I try to consider this quantity here. Double summation I goes from 1 to k, j goes from 1 to n, y I j minus capital Y bar whole square. Now I try to do here that here I try to add and subtract here y bar I. So now this can be written here as a y I j minus y bar I, and this y bar I and y bar can be clubbed here. And when I try to expand this square, so this will become here double summation square of this quantity, that is y I j minus y bar I whole square plus n times y bar I minus capital Y bar whole square. Because If you treat, this will be your here summation over ij y bar I minus y bar whole square, and so this is independent of here j. So, j is going from here 1 to n. So, this becomes here n times this quantity, and the cross product term that you can verify, this will become 0. Now, if you try to look at the structure of this factor, this first factor, what is this? Do not you think that this component looks like as if you are trying to compute a quantity like s square based on the sample mean of the ith sample? So, do not you think that that this looks like as if I am trying to find out a quantity like s square within the sample, right? So, this I can indicate by here s square w s y, within, w means here within, and systematic is here systematic, s y means systematic, and then I can adjust it by here k into n minus 1, so that it becomes similar to the definition what we have been given for say different types of s square, right. So, this quantity here s square w s y, this is here defined by like this 1 upon k into n minus 1 double summation I j y I j minus y bar I whole square, and this is the variation among the units that lie within the same systematic sample, right. Means if you try to see here that you have in this example which you have taken, you are simply trying to find out here the variance of all these units with respect to y I. Right. So, now once I have obtained this thing, then I can write down this variance of systematic sample here using this s square w s y. So, I try to substitute this quantity here, right, and you have to remember here one thing. What is here capital S square? This capital S square is the quantity which is based on all the units in the population, right. So, now I can rewrite this variance here as say like this: variance of y bar s y is equal to n minus 1 upon capital M times s square minus k into n minus upon n capital N s square w s y. And now, if you try to see here, this is a very important thing that is going to give you a very important conclusion. For example, here this n is going to be here n k. So, this k and k get cancelled out, and I have here capital N minus 1 upon capital N times s square minus small n minus 1 upon small n s square w s y. So, if you try to see what is here this quantity, this quantity is indicating the variation as a whole, means you are trying to take all the units in the population, because this capital S square is based on all the units in the population. And what is here this second factor? The second factor, do not you think that it looks like that that it has been pooled, it is just like a pool within variation of the kth systematic sample, of those k systematic sample. Now, if you try to look at the structure of this variance, try to look at this expression. You are trying to say here that this is the first factor is the variation as a whole, and then try to look here is a negative sign, minus sign. So, you are trying to subtract something from the total variation, right. And suppose in case if your s square w s y becomes 0, then it is going to be simply n minus 1 upon n capital S square. But do not you think that by looking at this expression, it means I can say that in case if this within variation is large, then variance of y bar I will become smaller. This means higher heterogeneity makes the estimator more efficient. That means In case if there is a higher heterogeneity in the sample, that means there will be higher heterogeneity in the estimator, and if the variation within the sample is increasing, then the variation of the variance of y bar sy is becoming smaller, right. And if you try to see, that is expected in the case of systematic sample. Why? Because in systematic sample you have no option to select your units according to your way. You are simply trying to choose a number and then you are entering into the population, and then you are going to select the unit at some pre-specified intervals. So, you can expect that the variability is going to be higher. So, now you are trying to propose here an estimator y bar sy, which is estimating the population mean in such a way such that the variation becomes smaller. And now if you try to remember, when we had discussed in the first few lectures that in systematic sampling or in sampling theory, I would say one of the important objective is that we always want to control the variability. We always want the estimators to have a smaller variance, and when you are trying to estimate the population mean, then we are going to use different types of sampling scheme, and our motive is that those sampling schemes have to be defined in such a way so that estimator of the population mean, which is dependent on them, should give them a smaller variance. And at that time we had discussed that there are 3 stages in which the variability can be controlled. One, before the selection of the sample, after the selection of the sample, and during the selection of the sample. So, before the selection of the sample, you have done sampling scheme like say stratified sampling, simple random sampling, etc. After getting the sample, you have used the ratio method, regression method of estimation, etc. to improve your estimator, and now you are trying to control the variability in systematic sampling when you are trying to draw the sample. Right. So, during the time of collection of the sample, you are trying to control the variability, and this is the reason what I said in the beginning of the lecture, how to ensure that even if you are getting a sample in this strange way, but still you have to ensure that you are getting a good value of the population mean. So, now you have seen that you have defined your y bar sy as an estimator of the population mean, and this is going to be an unbiased, and it is expected to give you a value with a smaller variance. Right. Now, if you try to see, if you remember in the case of cluster sampling also, we had discussed that whatever is the variability within the group, that is going to affect the efficiency. And in order to understand that thing, we had taken the help of intra-class correlation, and we had expressed variation in terms of intra-class correlation. So, the same thing we can do here also, because now you already have established that this systematic sample is just like you are trying to draw one cluster in case of cluster sampling. So, now we would like to consider the variance of this y bar sy, and we would try to introduce the term of intra-class correlation, so that I can find out the variance of y bar sy in terms of intra-class correlation. Okay. So, once again I will try to use the same mathematical technique that we had used earlier. I will try to use the fundamental definition of the intra-class correlation, and then I will try to substitute a term in the variance of y bar sy through that intra-class correlation. Right. So, if you try to see here the variance of y bar sy that we have obtained, it is here 1 upon k summation I goes from 1 to small k y bar I minus y bar whole square. Okay. Now, this can be written here like this. Suppose I try to write down here y bar I like this, and then I can write down this expression as say 1 upon k n square, this n comes out of this bracket, and this becomes say summation I goes from 1 to k, and then square of summation j goes from 1 to n yij minus y bar. And if you try to open this thing, then what will happen? This will become here summation j goes from 1 to n yij minus y bar whole square plus its cross product term, double summation j goes from 1 to n, L goes from 1 to n, and j is not equal to n, yij minus capital Y bar, yil minus capital Y bar. right? And if you try to bring this summation sign inside, then it becomes here, say this quantity will become nk minus 1 times s square, because if you try to see, this is here like this 1 over n minus 1 double summation ij y ij minus capital Y bar whole square, and here is small nk. Right. So, this quantity becomes nk minus s square, and this quantity becomes here a term with triple summation over I, J and L. Now, means if you remember that in the case of intra-class correlation in cluster sampling, we also have had a similar type of term which we had replaced by the term of intra-class correlation. So, first we try to just redefine the intra-class correlation, also although we have done it earlier, but just for the sake of understanding I am doing it here once again, and I am trying to express the intra-class correlation coefficient in terms of these three summation. So, if you try to see the intra-class correlation between the pairs of unit that are in the same systematic sample, it is defined by, now I am writing here say rho w. So, that means rho within systematic sample, expected value of y ij minus y bar, y il minus y bar divided by expected value of y ij minus y bar whole square. And this rho w lies between minus 1 upon nk minus 1 and 1. Now, this expected value of y ij minus y bar, y l minus y bar can be written here like this 1 upon nk into n minus 1 triple summation y ij minus y bar, y l minus y bar. And this quantity in the denominator here, this can be written here as nk minus 1 upon nk s square, because I am using here capital N is equal to small nk. So, now I can just obtain the value of this expression in terms of here rho w, and I try to substitute it in this expression over here at this place in the variance of y bar s y, right. So, if you try to do it here, then you will get here. Okay. So, now this variance of y bar s y will be obtained here like this. I simply have substituted this value over here. So, now you can see here this is a function of here rho w, which is the intra-class correlation coefficient between the pairs of unit which are in the same systematic sample. So, now you can see here by looking at the value of rho w, you can make different types of conclusions. Okay. For example, if you want to compare it with the simple random sampling without replacement, then we know that in case if you take a sample y1, y2, yn, can the variance of arithmetic mean of those observation which I am indicating here as a y bar SRS, this is given by capital N minus divided by capital N small n into capital S square. Now, I am trying to use here capital N is equal to here nk, right. So, I can write down here this expression as say k minus 1 upon capital N S square, and you have obtained the variance of systematic sample here as a like this one, right. So, now I can compare both of them, and if I try to take the difference between the variance of y bar SRS minus variance of y bar systematic, then this comes out to be here like this. And if I try to solve it, this is simply small n minus 1 upon small n s square w s y minus capital S square. So, now you can see the positivity or negativity of this entire expression depends only on this. Yeah, n is always going to be greater than 1, that is obvious, right. So, now I can conclude by looking at this expression that this variance of y bar s y is going to be smaller, or y bar s y is going to be more efficient than the sample mean of simple random sampling when s square w s y is greater than capital S square, and y bar s y is going to be less efficient than the simple random sample arithmetic mean when this s square w s y is smaller than s square, and obviously both are going to be equally efficient if s square w s y is equal to capital S square. So, now here in these cases you can see that I have tried to compare the sample mean obtained from simple random sampling and systematic sampling, where I have used the definition of this capital S square and say s square w s y. And yeah, that is giving you a fair idea that if the variation within the ith sample is smaller or larger, that is going to indicate the simple random sampling is a better option or systematic sampling is a better option. Okay. Now, now since I already have drawn or I have obtained this variance expression in terms of intra-class correlation, so why not to compare their variances with respect to the intra-class correlation of coefficient. So, I try to find out the relative efficiency of this y bar sy with respect to y bar SRS, that means the sample mean under simple random sampling without replacement. So, I try to define here the relative efficiency as the ratio of the variance of y bar under simple random sampling without replacement and variance of y bar sy. And now what you have to do, you simply have to substitute the values or the expression for these variances, which I have done here, right. These are the same expression that you have obtained. And yeah, means variance under y bar SRS WOR, that you know, that is capital N minus small n divided by capital N into small n times capital S square. So, if you simply try to substitute these values here and try to simplify it, you get here a term like this one, capital S square gets cancelled out. This is, now you can see, this is a function of capital N, small n and intra-class correlation coefficient rho W. So, now you know that this factor is always going to be positive, and if you want to make it in terms of the systematic sampling, then you simply have to replace this capital N by small n into small k, which is the population size under the systematic sample, and then you can see here we have this expression. So, this quantity is always going to be greater than 0, no issues. The only factor which is now here left is this one, and the range of rho W are between minus 1 upon nk minus 1, which was actually here, this is actually capital here capital N, and 1. So, now depending on the value of here rho W, we can make different types of comparison of systematic sample with respect to the simple random sample. So, I can now say that this y bar sy is going to be more efficient than y bar SRS when intra-class correlation coefficient is smaller than minus 1 upon nk minus 1, and it is going to be less efficient than y bar SRS when intra-class correlation is coefficient is greater than minus 1 upon nk minus 1, and both are going to be, that means y bar systematic sample and y bar SRS, both are going to be equally efficient when rho W is exactly equal to minus 1 over nk minus, right. So, now you can take a call that in a given situation you have whether simple random sampling or systematic sampling, you can look into the value of this this intra-class correlation coefficient, and you can take a call that which of the estimator is going to give you less variance, right. Okay. So, now we stop in this lecture, and you have seen here a wonderful thing, that even when you are not planning anything and then you are trying to take a sample without prior planning, you are simply jumping into the forest and then you are trying to select, say, this every ith unit, and based on that, in case if you try to estimate the population mean using the estimator y bar sy, then you are going to get a good value, that is going to be an unbiased estimator, and that will have a smaller variance. By looking at the expression of the variance of y bar sy, you can be confident that this expression has been obtained in such a way, that means the sample mean under systematic sample has been obtained in such a way such that even if you are trying to take the sample in such a way without any prior planning, still that is going to give you a value with a smaller variance, and that is the beauty of this systematic sampling, right. So, now you have seen that this is a different types of sampling scheme, and yeah, this is also a methodology to draw the sample under a different type of condition. For example, you have considered simple random sampling, stratified sampling, cluster sampling, etc. Similarly, this is also a sampling methodology. So, now I would request you that you try to look into these things and try to find out these expressions yourself without looking into the slides or the notes. and that will give you more confidence. And in the next turn, I will try to compare this systematic sampling with the stratified sampling, and based on that we will try to discuss some more results. Okay, so you practice, and I will see you in the next lecture. Till then, goodbye.